Tom Wagner is going to tell you a little bit more about the Earth's frozen environments.
Yeah, and if we could have the first slide. I thought we'd start with just a really brief description of ice shelves, which, as Brittany pointed out, is probably our best analog for what's happened with the ice on Europa. And what happens is this: you take a place like Greenland or Antarctica, you build up a lot of ice and snow in the middle until it literally gets miles thick. And then it begins to flow out to the sides, just like if I poured honey on the table right here, how it would flow out. Well, what happens when that ice hits the ocean is it begins to float. And that floating glacier is what an ice shelf is. They can be many hundreds of feet thick. They can extend out many miles, hundreds of miles in some cases. In fact, the Ross Ice Shelf is the size of France in Antarctica. Next slide. But ice shelves are also remarkably dynamic features. Most people had thought they were kind of stable, but here we saw in 2008, the Wilkins Ice Shelf in Antarctica, literally over the course of a couple of weeks, it blew apart in what my colleagues describes as the mosh pit. And what happened was this ice, as it flowed out, it got a little thinner. Eventually, it triggered a collapse, which then triggered a further collapse, and it tumbled away like giant dominoes. Next slide. Some of these dominoes, though, are miles long and hundreds of feet thick, and they turn over and rotate. And also, as Brittany pointed out, that matrix material that we see on Europa probably would look something like this, which is brash ice, which is the broken up bits that fill in between these bergs as they bump into each other. Next slide. This process is profoundly important for us on Earth also, and this example is the Larsen Ice Shelf, which is on the Antarctic Peninsula that extends up towards South America. In 2002, an area the size of Rhode Island again collapsed just over the course of a couple of weeks. Picture giant tablets just tumbling away, things hundreds of feet thick, right, over a giant, like as big as a US state. What happened, though, that was so remarkable was that the glaciers on the land behind it, off to the left side of the screen that you're looking at, they sped up dramatically as you kind of popped the cork or pulled away this ice shelf. Some of them increased their speed 8-fold. They went so fast that they drained all the ice that was behind them, and the surface deflated by over 150 feet in some cases, over 600 feet in other cases, just over the course of 5 or 6 years. So this is really important because when we try to project future sea level rise on the planet, we think that this is probably the most dynamic element that we have to take into account because there's ice shelves all around Antarctica. Next slide. And this is one of the most important ice shelves for that sea level rise work that I spoke about. This is the Pine Island Glacier Ice Shelf. And we have studied these processes in great detail. And one thing you should realize is that it's not a huge extrapolation to go from what we're doing on Earth to Europa, because we have satellites and aircraft where we can study these things all the way down to the base levels. In this case, what you're looking at, the gray is the surface of the ice shelf, which was shot by LiDAR from an aircraft, literally a little laser rastering over the surface. Underneath that, the next layer, that kind of mountainous colored stuff, is the base of the ice shelf, which was with radar. As amazing as it sounds, we can put a radar under an airplane and map the structure of the ice and the bottom of the ice. Under there would be the ocean, and then the bottom is actually the sea floor, which we map by a gravimeter. It's really important to us because, again, like the Europa case where you have warm water that's causing melting and fracturing in things, what our big fear on Earth is that warm water in the ocean is getting underneath these ice shelves and destabilizing them. And what we have to do is we have to get the topography of the under ice shelf, we have to get the topography of the seafloor to understand how coastal waters mix in. Next slide. But the last slide that I want to show you is actually a radar image over a subglacial lake, literally like one of these perched lakes we're talking about on Europa. In Antarctica, there are over 140 of these lakes. It was shocking to me. I started working in the Antarctic world probably about 7 or 8 years ago, and we didn't really know there was that much water around. And now through radar studies like this, that vertical scale is about 4 kilometers. And you see the flat line in the bottom? That's where the radar waves have bounced off the surface of the lake. That lake is the size of Lake Ontario. And with that, I'll pass off to Tory, who's going to tell us about habitability on Europa.
Thanks, Tom. So one of the things that makes Europa so exciting, that has made it such a compelling object of study for decades, is the presence of this liquid water ocean that meets one of the critical requirements for life. And what you're hearing about today from Brittany bears on a second of life's crucial requirements, and that is the requirement for energy. So habitability is a concept that we all can relate to personal experience as living organisms. Anybody on the street could give you a pretty good accounting of what it takes to stay alive: water, food, shelter, air to breathe. So if we think about these things in the context of Europa, there is absolutely no shortage of water there. That we know and have known for more than a decade. As far as we know, the environment is relatively sheltering if we think about shelter as the set of conditions that allow life to persist in an environmental context. Most of what we can conceive as a potential European ocean chemistry would be reasonably suitable for life. But the big and open question has been one of energy. And when we talk about food to eat and air to breathe, what we're really talking about is our requirement for energy. And I've tried to conceptualize how to think of this in terms of a figure. So you could view Europa as something like a great big battery. It's stored energy. And the question has been whether or not that stored energy is actually available for life on Europa. So if you took a normal D-cell battery and cut it away, what you would see is chemically different layers that are isolated from one another. It's energy that's stored, and the way to tap that energy, as you can see in the second slide, is to connect the terminals. When you connect the terminals with a wire, electrons flow from place to place. That flow of electrons is what we call electricity. But in essence, what's happening is a movement of material from the outer layer to the inner layer that serves to release energy. So in the next slide, you can see that we can view Europa in much the same way. We know from spacecraft observations of surface chemistry, from inference of the chemistry of Europa's crust, that it represents, in essence, stored energy. But with this big, thick, 10-kilometer or more ice shell, the big open question has been, does that energy ever get released? Is it ever available in the ocean? What you're hearing about here today, if we can have the last slide, would be a way to take this surface material, transport it potentially down into the ocean, and in essence tap Europa's battery. When you tap that battery, you've moved from a system that checks one of the requirements for life to a system that checks a second critical requirement for life. And I think this really impacts the way that we consider habitability on Europa. So how should we view this in the big context of European ocean exploration? I think Louise is the person to address this.
Thank you, Tory.